Hello everybody, it is May 27, 2020. Time is 1420 CDT, which is 1920 UTC. It is 82 degrees Fahrenheit out, which is more than 25, 27, 28 degrees centigrade out, and it is Geo-Rant time. But first, I need to talk about something important. And you may see this. It's about an hour and 10 minutes from an historic event, from the launch of astronauts from the United States using American design craft into space since 2011. With the retirement of the space shuttle, we will no longer be relying on the Russians to launch people to the ISS. All right, so I think it's safe to say at this point it's not going to be canceled. But anyway, what is this Geo-Rant about? Well, I'm going to talk about sedimentary rocks. I'm going to go back to the Precambrian. You guys have heard me talk about before about plate tectonics and how it was not in operation in the Hadean. And I don't know what it is with humans. We have this innate need, this innate lusting for some reason to take what we see around us today, what's familiar to us now, and push it as far back into the past as we can. And I don't understand this. Plate tectonics isn't the only thing people do this with. People do this with stuff all the time. And it's not, plate tectonics was not in operation during the Hadean. I mean, there is no evidence of that. We don't have, and I'm going to talk briefly about stuff. I'm going to talk about the steep rock group, specifically the carbonate. But first, I need to talk a little bit about the rocks in general. Now, many of you know about the Jack Hills and the oldest zircon that was taken from there. I mean, there's one at 4463 million years old MA, but that one's conjectural. But the pretty much standard, or the pretty much oldest accepted one, is 4404 plus or minus 8 million years, and that is in a conglomerate, a metaconglomerate. It is a detrital zircon. The actual conglomerate itself was probably deposited around 3 billion years ago, so a lot later. Remember, detrital zircons are included as the sediment is deposited before it becomes lithified new rock. It will grab grains and become laid down and become rock eventually, but it brings those grains from the chemically and mechanically eroded rocks, and it will bring those zircons. So you can be younger than your youngest zircon, but you cannot be older. So that is the oldest detrital zircon known presently, is within the Jack Hills, and that was pulled from, we don't know where. We have no rocks that are 4.4 billion years old that we know of, that are igneous or derived from igneous rocks, like meta-igneous. Okay? We have something close to that. Well, first there's the I'm going to butcher this, NUVVUAGITTUQ Greenstone Belt, which is in Quebec, Hudson Bay, Quebec. And the zircons, that is another contender for the oldest rock on Earth, but that's highly contested. And that is, I believe, that is an meta-igneous rock. And the ages vary wildly from 4388 million to 3750 million years old. And it could be inherited zircons in that as well. So that one's still out in the open. We don't really know that one. But the oldest known cooled from magma rock is the Acasta gneiss on the Slave Craton in Canada. Okay. That had one at 4031 plus or minus 3 MA. Other dates have been more around 3300. But that 4031 plus or minus 3 is probably pretty solid. And these are the sources I'm getting this stuff from, about this background, the Jack Hills, Acasta, and other stuff. You can stop, look at it if you want. I will give it to you in a second. But I just needed to touch on that and make clear the very fact that the oldest known zircon, the oldest known date derived from a rock is not a rock that was cooled directly from a magma. It has been transported. It's within a metaconglomerate, okay? So we don't have any 4 billion year old, oh, that's blank, ones except for the cast of gneiss, okay? So whatever was going on Earth was distinctly different from what is going on today. And you could sit there and argue, yeah, the further you go back into the past, the less likely you are to have a geologic preserved record, and that's true to some extent. But what I'm going to talk about here, on the order of about 3 billion years old, we start to see actual evidence of plate tectonics. Remember, back in the Hadean and even through a large chunk of the Archean, we don't have any real true granites, and that's rare today. They have something called TTGs, and I've talked about these before, and those do still happen, but they're not common like they were. But anyway, I'm going to talk about the steep rock group. And why am I talking about this? Well, because, if plate tectonics was in operation during the Hadean, and then around the Paleoproterozoic, 2.5 billion with a B years ago, we start to see well-developed passive margin sequences like the Huronian supergroup and analogs in South Africa, the Snowy Pass and all this stuff. We start to see this stuff. So and we start to see flights and stuff like that common. So we're pretty confident. I mean, and the Huronian supergroup pretty much represents a full Wilson cycle, that with the Pinokian. So we're pretty confident plate tectonics pretty close to something today was in operation then. But there's this gap. This gap between 3.8 and 2.5 billion years ago where something was happening. Well, like most things, sorry, I apologize for that. I'm having sinus issues again. Like most things, there isn't a line where you can sit here and say, yeah, the Earth wasn't having plate tectonics, then it did. Here's the day, time, stamp, and all that. You can't do that. There was likely a transition period. Was the period 10 million years? Probably longer than that. Was it 100 million years? Probably longer than that. Was it 1 billion years? Probably not. We do see, like with the steep rock group, and this is still somewhat argued, that there was something close to plate tectonics already in action. And it is generally accepted that the steep rock group, the sediments that I'm going to talk about, were deposited between 2801 and 2780 million years ago. So we're talking Neo-Archean. We're talking just before the Paleoproterozoic. So we're not kicking back plate tectonics too far into the past. But there is strong evidence that at about 3.1 billion years, we start to get at least some plate tectonics in action. Doesn't mean it was happening globally, because we don't even have continental reconstructions until 3 billion years ago, and those are questionable. And and by the time the Paleoproterozoic, we start to have continents. Okay. But anyway, this steep rock group is underlain by the Marmian complex, which is a meta-TTG, and it's been dated between 3003 and 2928 million years old. So that's the oldest these sediments can be. Then on top of it, we have the Wagata Formation, which is mostly conglomerate and sandstone with some shale in it. The Mosher carbonate, which is broken down to 2 members, but I'm not going to divide them here. And then we have this Jollifree ore zone, which is BIF, Banded Iron Formation. And remember, BIFs were very common in the Archean, and then through the Paleoproterozoic as well. But by the time we get closer to today, like past the 1.85 billion year mark to today, they all but disappear. And by 800 million years ago, they're gone. Okay? So we had whatever favored pre-plate tectonics really favored banded iron formation. Now I know correlation isn't causation, but that's kind of a big thing. And also, before the Paleoproterozoic, we don't see a lot of carbonates. This is one of the exceptions, is the steep rock carbonate, okay, that Mosher carbonate, okay, but they are there, obviously. We do have Archean carbonates, but they don't become common into the Paleoproterozoic, because we usually need, you can get carbonates in lake and deposits and floodplains of streams and stuff like that, but we think the steep rock, the sedimentary parts, were a marine platform. And I'm pulling all this information from these 3 Actually, the first two up here. Now, it's very complicated tectonically. We suspect in cross-section, this is something, how it looks. So when this was deposited, this stuff would have been the stuff from, where is it? From here down would have been deposited this way, but now it's vertical. So we had some sort of orogenic event, something that was probably likely related to subduction at the end of the formation of this platform. Now, the platform itself is very conducive. It contains a lot of stromatolites, I think especially at the base. But while it was being deposited, it's modeled something like this figure on the bottom here. I hope you can see it. Let's go focus for a second. Okay. And that would be typical of a, I don't want to say passive margin sequence. It does vary a little bit. There's a lot more paleotopography, but there seems to be, it seems to be associated with some sort of rifting event, okay? And it is overlain technically stratigraphically by the dismal ash rock and the Witch Bay Formation, which some people don't include in steep rock. It's arguably that it's not, but the consensus is it is part of the steep rock group as of now, because there's that big tectonic shear zone that's more like a melange, which just means it's a shear zone with a lot of breccia and a lot of weird structures, and you can't tell heads from tails. Even structural geologists have a hard time figuring out your stress fields, and stuff like that. I personally think you should just put the sedimentary ones in there. You can make the other two formations their own group if you wanted, but I'm not going to explore that. So, but this carbonate platform, if it was laid down between 2801 and 2780 million years ago, that's 21 million years of deposition. And we have dates, like I said, the dismal ash rock above the BIF is 2870. So that we have a bracket there. And it's hard to find thickness on this because of the deformation, but the thickness of the steep rock sediments, the Wagatah Formation, the Mosher Conglomerate, and the Jalafree Ore Zone is maximum, although it seems to be thinner than this in most places, about 900 meters, which is 2,950 feet, or between, or close to 0.55 miles, okay, in thickness. Now, that's a lot of sediment to deposit in 20 million years, but this is common in the Precambrian, especially in the Mesoproterozoic. And I've talked about this before when I've talked about the Belt Supergroup and the Sibley group and stuff like that. But it's not erroneously thick to things like, compared to like the Sibley group and stuff like that. Sibley group is about 16 kilometers thick, and it was deposited in apparently about 90 million years. And this is 20 million years, and it's not even a kilometer thick. So it's not out of the realm of possibility compared to other basins. So it probably did represent some sort of platform, whether it probably wasn't intercratonic either. It probably was a margin. How do I know it wasn't an intercratonic basin like, the Illinois basin or the Michigan basin? Well, because we have this, we have that budding up, that complex, we have that, what appears to be subduction up against that shear zone that separates the Jalafree from the dismal ash rock, okay? So we have what looks like a normal passive margin sequence, but instead of having dominantly shales, because in a passive margin sequence, you get sandstone, you go further out, you get shale, and you get carbonates. Here it's a little different, but like I said, it was a different time. We had a strong BIF above it, and, we don't have any BIFs today. But it does kind of look like that, and, the rocks underneath could have represented some sort of tectonic, some sort of stretching of the plates, and that shear zone does look like an orogenic event occurred. And there's other places in Ontario, this is in Ontario by the way, where you see these belts, these carbonate belts, and they all may be correlative. There may have been one tectonic front during the assemblage of the Superior Craton, so internally. So this kind of looks like plate tectonics in action. Now, remember, I said we have a transition zone. If, there could have been something else. This could look like plate tectonics, but it probably is. There's lots of lines of evidence that suggest this was. But you got to remember, plate tectonics has a specific definition. And I've posted this before, but basically, you have the Earth, you have rigid crustal lithospheric plates. Those plates move about the globe. Subduction, you get a rift, they spread apart at spreading zones, you get subduction back into the mantle. Now, these plates follow along Euler poles, and that's a talk for another time. But just because we have some resemblance of plate tectonics doesn't mean that it goes all the way back to the Hadean. You can't keep extrapolating back in the past without solid evidence like that. I mean, it just doesn't make any sense. So this is 15 minutes. I don't want to give this too much longer. So this steep rock group does look like plate tectonics in action, does look like a Wilson cycle. We don't seem to have the volcanics at the base that I'm aware of, the spreading center, but this could have just been extension and a sea could have come in and you just could have had some sort of, because the lithosphere then had to be more malleable. It wasn't as rigid as it is now. So remember, I mean, there's that transition zone, and I would place the transition from non-plate tectonics to plate tectonics somewhere between 3.8 and 3.2 billion years ago. And this would be one of the first things showing plate tectonics, but you still have some residual non-plate tectonic type things going on to about 2.5 billion years ago. And there's all sorts of hypotheses as to what was in operation before. And you can have things that look like subduction. And the reason why people keep trying to push plate tectonics back is because they keep seeing minerals associated with water. Well, Earth has had water on its surface for 4.1 billion years. That doesn't mean you have an active subduction zone, and that doesn't mean that plate tectonics is a modern subduction zone where plate tectonics is globally active. That doesn't mean that. There's many ways to get water down into the mantle, okay? Or down into the lithosphere, at least. So anyway, I think I'm going to cut this off. I made this long enough, but if you have any questions or comments, please leave them below, and I hope you learned something. I hope this one wasn't too long, and I need to make these shorter.